In the final tutorial, I'll be going over this idea of autonomous scientific discovery, also referred to as self-driving laboratories or Lab 4.0. Goes by a few other names, but this idea of incorporating many of the concepts that have been described previously with this efficient optimization and efficient adaptive experimentation, and combining that with autonomous experimentation using, for example, robots and other sensors and devices to have a fully closed loop uh, research campaign where the researcher, you as the researcher, define the scope of the campaign, set up all the hardware, and then essentially let it run and autonomously optimize. And then, if necessary, you can step in or change things, kind of instill some of that human intuition into the search, uh, to kind of have this collaborative environment. But the idea that you, as a scientist, free up more of your time for higher level tasks, and then allow this autonomous experimentation to carry out and spend more time on deciding on new campaigns and analyzing the results from the experimentation. So I'm going to be going over a demo for this, one that I created uh, in order to act as a teaching and a prototyping platform for these self-driving laboratories. Um, and I'll be showing you a Jupyter notebook that interfaces with this, doing cloud-based experimentation, as well as some of the source code for the microcontroller that runs it as well. So let's go a little bit more into the motivation behind self-driving laboratories. So this notebook, I'll be running you through that demo that I mentioned. And I mentioned briefly that Lab 4.0 concept. And in industry with manufacturing, there's something that's often referred to as the fourth industrial revolution, or Industry 4.0. And as it says here, it's revolutioning the way companies manufacture, improve, and distribute their products by integrating new technologies, including Internet of Things, cloud computing, and analytics, and AI and machine learning into their production facilities and throughout their operations. And this is accelerating the efficiency that which manufacturers are developing products. However, those products themselves are limited by the materials that make them up. And discovery of new materials, these could be plastics, alloys, molecules, and drugs, that is typically a very slow process, and traditionally has been by manual trial and error and by accidental or serendipitous discovery. So, what's in common with all of these materials pictured here? The answer is each of these were discovered accidentally. And so there's this question of what if we could bring the acceleration of Industry 4.0 to a scientific research laboratory setting? And that's where the concept of self-driving laboratories come in. They're autonomous research laboratories that learn from prior experiments using artificial intelligence, automatically carry out those next experiments, and discover new materials in a fraction of the time and at a fraction of the cost. We could be looking at a reduction from 20 years going to market down to as little as 1 year, and as much as $20 million to as little as a few $1,000,000. And this frees up time for the researcher to focus on higher level tasks that are about designing the campaigns, analyzing the data, and formulating new hypotheses. This kind of gives you an idea of what that loop will look like, where you have your prior knowledge as the researcher, use the researcher, establish the objectives and the constraints and that search space. And then on the materials acceleration platform side, basically one of these self-driving laboratories or a high throughput experimentation setup that helps accelerate the discovery of new materials or new scientific knowledge, is that we have this intelligent experiment selection, one option being Bayesian optimization, and then you have robots or other automated equipment running the actual experiments, performing some analysis, and repeating that loop there. And the human understanding really comes in designing the campaign itself and maybe involving making some changes as the optimization progresses. If the uh, algorithm starts discovering silly answers, things that aren't really what you expected based on the search bounds that you defined, you could be restricting those search bounds and kind of resetting the campaign, or updating the campaign as it's going on, with the desired results of these loops being to create new functional materials, bring the materials to market quicker and for less cost, as well as to discover new scientific knowledge. So there are a few different notable examples and many more being produced each year of these self-driving laboratories. And these are helping to address very urgent societal needs, which cover these broad categories like climate change, energy, even food and agriculture. And just taking a look at some of these videos, you can imagine that the cost of creating these systems and creating these laboratories is high, both in terms of the expertise required, as well as the actual monetary cost and the setup time and troubleshooting, all of that. What the community has done is developed a series of different prototyping and teaching platforms. You've got this Bayesian optimization bartender, or Bob, and different experiments done by the Cronin laboratory. You have some open source solutions like OpenTrons, and Lego Mindstorm kits or equivalents being adapted, 3D printers being adapted, and all sorts of really great teaching examples. For even increased adoption of this, there needs to be something that's lower cost, easier to set up, and has a fairly small footprint while still retaining those key principles of a self-driving laboratory. And so here we have this idea of a self-driving laboratory that uses no chemistry, no materials. It just uses light, but still captures a lot of the principles of a full-scale, real-world task laboratory. And in a nutshell, what this does is it takes, you have a dimmable red, green, blue set of LEDs that you can control the brightness of via a microcontroller. You measure the intensity of that light at discrete wavelengths, and you define some target spectrum that you want to match. So this is a color matching task. That's the optimization problem or objective. And you try to minimize the difference between the target spectrum and what you measure, and use cloud-based physics simulations to help guide the algorithm, and use AI, different machine learning methods such as Bayesian optimization, to iteratively decide on the next experiment to run or the next batch of experiments to run. And here's what the actual prototype looks like for this kind of closed loop mini spectroscopy laboratory. And I have that right here as well. One example of this being put together. And so here you can see that we've got an LED, red, green, blue set of LEDs. We have the light sensor here that gets positioned over the LEDs. We have our pico wireless microcontroller, which fits into a kind of educational kit and base, the MakerPi Pico. And we upload our source code onto the Pico microcontroller. It connects to the internet, and then we can send commands over a framework called MQTT. It's a standard in Internet of Things style communication in order to control the brightness of each LED, and also measure the light sensor data there. So next, I'm going to show you what the source code on the Pico wireless microcontroller looks like, and then I'll go over how to communicate with the microcontroller over a Wi-Fi connection. So we have a whole bunch of things that we're importing. We have JSON for working with one of our data types, converting these dictionaries, Python dictionaries, to a JSON format for doing some communication. We have a password and a name of our Wi-Fi called an SSID. We use some different timing functions, some things to help us connect to the Wi-Fi network here, as well as a class for the light sensor and a class for the RGB LEDs. And then of course we need this MQTT client, which will facilitate us doing the Internet of Things style communication between devices and clients via the Mosquito MQTT host. So we'll create our ID, which will be specific to our Pico wireless microcontroller. Each one will have a unique ID. We have a prefix that helps us to define our topic that we will subscribe to on the MQTT platform. We have our pixels and our sensor, or in other words, our LEDs and our sensor. And we have an onboard LED that will flash as sort of a sign of life later on. We have each of our discrete channels here, the wavelengths corresponding to each channel. During this next portion, we'll connect to the network and retry if there's an issue, and print an error if it isn't able to connect. We'll also use an onboard buzzer that's on the MakerPi Pico base to signify the start of an experiment. Again, just another kind of sign of life thing that it's working, and the auditory notification. We have a function that helps us to get an error traceback to be able to diagnose problems if they come up. If some error happens on the Pico wireless side, that we can get that error returned to us in whatever, in a Jupyter notebook or whatever we're using to send commands to the Pico microcontroller. We have a function for validating the inputs to make sure the inputs aren't violating something that could go wrong. This would be really useful in a case where you have moving components and you want to make sure to constrain whatever inputs are there to safe values. So let's say you have a robotic arm and you want to restrict the movement to certain levels or certain speeds, or you have a dispenser and you want to limit it, make sure that the dispenser isn't run on full power. Other safety measures can be put in place here, as well as things that help restrict the experiment to the search domain that is relevant or necessary, and make sure that you're not sending some input that will throw an error. For example, sending a string when it was expecting an integer, using incorrect data types and so forth. We'll also have a way to reset the experiment, which turns off the LED. And we have a function for what happens when subscriptions to the MQTT get renewed, which is just subscribing to the topic that we had before and saying that this is on, adding this GPIO part of the string there. And QoS is kind of a nuanced topic, but it essentially, the different levels of this quality of service determine how robust the communication between a client and a device are. Whether they kind of do this handshake to make sure that the data was received only once, or whether they just make sure that the data gets received at least once, or if it just doesn't even check and it just tries to send it once, and if it does or doesn't get received. And that's this QoS 0, is that it sends it, and if something goes wrong, it doesn't handle the error there. So with our callback function, and maybe go into that, it's not implemented for some of the MicroPython, this microcontroller specific code, and it can also throw some unexpected errors when you do the more complex handshakes that take up more time. But so far, this has been working pretty well with the lower quality of service, at least on the microcontroller side. We have our callback function, which does a lot of the heavy lifting. And so we initialize the sensor data dictionary, and we use the message that was received from our topic and parse some of the data in there. So we extract the red, green, and blue values, the parameters that were requested. We also request some of these fidelity parameters like the time, the step, the gain, these other things that affect some of the noise and other trade-offs of the experiment, but basically just sensor settings, whereas the RGB would be like the physical parameters of the experiment. We validate the inputs to make sure that things aren't out of bounds, that we're getting the right data types. We send a small beep to the microcontroller and then set the LEDs to the RGB values that were requested. From there, we make sure the sensor settings are set to what was requested as well, and then extract the data for each of the channels. We add each of those discrete intensity readings to the sensor data dictionary, handle any errors, and try to print and send useful messages if they're there. And once that's completed, we reset the experiment by turning off the LEDs, create our payload that we'll be sending over MQTT using JSON.dumps. So it takes this dictionary and turns it into this JSON string, I believe. And then we publish our payload to this AS7341, which is the name of the sensor, to that topic. We'll also have a few functions that just help out a little bit with making sure things don't disconnect and that things are running okay. So we have a heartbeat function that will essentially ping the network and make sure that we don't lose connection with the MQTT server because of a timeout. We have a sign up live function that will just blink the onboard LED, this small green LED on the Pico wireless microcontroller every, I think, 5 seconds or so. And then something else for just printing a message to help with debugging when a published message is received. We define our client with the prefix that we chose, our URL for the server, and we leave the user and password as none, but you can also implement something where you have a username and a password and some other authentication. And we connect to the client. We set our callback to that heavy lifting function that does the control of the experiment and reading the sensor data. And we establish our on connect and on message attributes for the client. And finally, we subscribe to this topic of interest, the GPIO topic that we defined earlier. And in a while loop, we will check for messages and then start, do that heartbeat ping to the server, as well as blink the LED if around 5 seconds has elapsed. So that's everything here. Essentially what you've created is a listener. So it will listen for messages on the server, and when the correct type of message comes in on a particular topic, then it will run through controlling the brightness of each of the LEDs. It will read the sensor data and then sort of reset the experiment and send the relevant data back. So once we have our code ready, we'll upload it to the microcontroller connected via USB here. And in the Thani application, which just makes it easy to upload code to microcontrollers like the Pico Wireless and other Arduino microcontrollers, Raspberry Pi controllers, and so forth. We upload our code, make sure that we have the proper credentials saved in this secrets.py file, and then we can either run it manually from here, or we can simply unplug it and plug it into a power source, just some wall wart, and it will automatically run this main.py program that we put on. Once we have that up and running, connected to a Wi-Fi network, and we see that the LED is blinking, we can go back to a Jupyter Notebook, and I'll show some of the lower level implementation here, as well as a package that I wrote that can serve as a template for writing up some of these communications between the microcontroller and Jupyter Notebook or Python script that you're running somewhere else, which could be on Google Colab, it could be on your machine. The main requirement just being that both whatever machine you're running the code from is connected to the internet, as well as the microcontroller that's running the listening code is connected to the internet as well. So here we just have some sort of boilerplate code that helps us know whether or not we're running it in Google Colab or if we're just running it somewhere else. And we're going to use this test string for the pico ID, which corresponds to kind of a hard-coded ID on a system that's set up in Salt Lake City and is publicly accessible. So normally this would be some string of letters and numbers that is unique to the microcontroller you're running on, but this has been hard-coded for a public test demo that anywhere in the world can access. That's what we'll be using here. We'll be using the PAHO MQTT client here, and we'll make a queue, a Python queue, that allows us to get kind of that running list of the experiments that need to be run. We define a timeout as 30 seconds. We also have this onMessage function, which will be triggered as a callback when a message is received. And for this one, we'll put our payload that, if you remember back to the microcontroller source code, when we encoded that payload, we'll convert it back to a dictionary using json.loads, and we'll put it into our queue each time. So every time a message is received, it goes into the queue. And then we have this helper function, observe sensor data, which is our way of sending a command and receiving the data. So you'll notice it takes a red, green, and blue input arguments, a pico ID, a session ID, and our host name, which is the Mosquito test MQTT platform here. We'll make a session ID if one wasn't provided. This is essentially just to keep track of the session that you're running the notebook. It's not required, but it's useful for checking to make sure things look okay. And I should say it is required here because that's one of the things we check for to make sure that the session ID matches when you send a message and receive it back. We also have an experiment ID that'll be uniquely associated to a particular run with a set of RGB values. We have our prefix for the topic, and then a topic for the NeoPixel, and a topic for the sensor. And you'll notice these look similar to or correspond directly to the topics elsewhere. The only difference here being that we've hard-coded this to the input pin 28, as opposed to leaving it as a wildcard hashtag, essentially. When the client is connecting, we'll subscribe to the sensor topic, and we'll use a higher quality of service to try to make sure that the message gets across. We'll instantiate our client similar to before, set our onConnect and onMessage attributes, and then connect to our host name, this test.mosquito.org, which is the same one that the microcontroller is connected to. We'll subscribe to our sensor topic. We will create our payload from our input parameters, which contains red, green, and blue. And the package has been updated since to include those other parameters, the a time, a step, and gain, which control some of the sensor settings. We'll also put our session ID and experiment ID in there, and we'll publish our payload to the NeoPixel topic. And we'll start a loop and essentially get, as soon as the sensor data queue receives a message from the onMessage function, we'll retrieve that, If it's waiting for more than our 30 seconds, it'll throw an error saying that the queue is empty. We'll extract our input message and make sure that things match like the session ID and the experiment ID. So we're not, if multiple people are sending messages, that they're not getting those messages mixed up when they receive the data. We check to make sure that the requested red, green, and blue values match what the function, the ones that were returned match the ones that were requested. And then we'll return that sensor data in this helper function here. So to see that in action, we can run observe sensor data using RGB values of 5, 10, and 15, respectively, using our test pico ID. So this will send commands to the public demo that's set up 3 times using these different parameters. And we'll notice that it's returning that sensor data for each of the channels for each of those 3 portions there. So we're in our home stretch now. For this last part, we'll be taking a look at using the Python package that wraps some of the functionality here with observing the sensor data and gets updated to accommodate changes to the code, changes to how data is written and stored in, say, a MongoDB backend. So here we will, it's already installed here. We'll move on to importing the self-driving lab demo class, as well as the appropriate observed sensor data function. We'll use the same test pico ID, create a random session ID, and use this auto load equals true keyword argument so that we perform our target data experiment automatically. And what this really does, what this class does is, first off, it can serve as a template for you to adapt to other self-driving lab examples, other experimental or simulation examples. And it also wraps the functionality of setting up the optimization problem and returning the objectives and taking care of some of the boilerplate code involved. So here we've got our SDL class instantiated. And we also pass an observe sensor data function that corresponds to our MQTT stuff that we showed above, as well as the keyword arguments for that function, being the pico ID and the session ID. And then just to demonstrate what we did before, we can observe the sensor data for a particular set of RGB values, return the data here. A physical experiment was run on the hardware, connected externally, so it's a cloud-based experiment, or at least cloud-based control of an experiment. We have this last hello world optimization comparison of grid search versus random search versus Bayesian optimization. We'll be using some convenience functions that are defined, and we'll use some search bounds as defined here for the red, green, and blue parameters. We'll use 27 iterations, and we'll run our grid search, random search, and ACTS Bayesian optimization, retrieve the results of that. And this takes around 6 minutes to run, 27 iterations for the 3 different search types. Compile all the results into a best error so far versus the iteration number for fair comparison of these. We should run it on multiple campaigns with different target spectra that are used for each of the campaigns. Provide some of that stochasticity there. And we can take a look at an example output here where we're looking at the best error so far versus the iteration number for the 3 search types. And we can also take a look at the points that were explored in each of the search algorithms for grid, for random, and for Bayesian optimization, as well as take a look at the best points versus the true red, green, and blue value that was used to produce the target data. Now, that tutorial went over some of the basics, this hello world of optimization, some of the setup on the microcontroller side, and communicating over MQTT in an Internet of Things style communication. Now, what's coming later in another set of recordings and tutorials will be applying the self-driving lab demonstration, this closed loop spectroscopy laboratory on, and combining those with the other tutorials that have been mentioned here with multi-fidelity optimization, multi-objective optimization, batch optimization, asynchronous optimization, and other advanced optimization topics, with the goal in mind of reducing the barrier it takes for someone to apply these advanced optimization topics, as well as uh, instill some trust and show how each of these advanced optimization topics can increase the efficiency over some of the other baselines, some of the things that might be more familiar but less efficient. And so, with the reduced barrier to entry and building some trust in what these algorithms are capable of, demonstrating those capabilities, hoping to really advance the future of chemistry and material science discovery tasks to address real world problems.